Section 2.1 Matrix Operations. First, we're going to look at some matrix notation. There are two ways to denote an n by n matrix A. The first way would be in terms of the columns of A, where we just list the columns as vectors, A1, A2, up to AN. And then the next way would be in terms of the entries of A. And so this is where we're kind of getting into some new terminology, where we have each term, we have A11, and then down here we have AMN. So we're listing the entries with the row they're in, and then second number is the column that they're in. So here we have row I, but it's column 1, whereas here we have row 1, but column J. A diagonal matrix is a square matrix whose non-diagonal entries are 0. So the main diagonal entries have the same number in the subscript. So like A11, and then A22, A33, and so on. We also have a zero matrix, which is just an n by n matrix whose entries are all zeros. We can multiply a matrix by a scalar, and we would just multiply each entry in the matrix by a scalar. So in this case, I want to multiply this 2 by 2 matrix by the scalar 2. And so every entry in that matrix gets multiplied by 2. We can also add matrices as long as they're the same size, and we add their corresponding entries. So in this case, we would be adding 1 plus 5 to get the 6, and so on. Let's look at theorem 1. We're going to assume that A, B, and C are matrices of the same size, and that R and S are scalars. So we have the following properties. A plus B is equal to B plus A. If we group them, A plus B as a group plus C is equal to A plus B plus C as a group. We can add the zero matrix. A plus the zero matrix is equal to A. If I multiply the sum of two matrices by a scalar, then I can essentially distribute that scalar to each matrix and then add those two up together. The same thing if I have the sum of scalars times a matrix, then I can distribute the matrix to each scalar and add those two together. And then we can change grouping with multiplying by scalars. So R parentheses S times A is equal to parentheses RS then times our matrix A. Now we want to look at matrix multiplication. If A is an n by n matrix and B is an n by p matrix, where B is just consists of the columns B1 through BP vectors, then the multiplication A times B is the m by p matrix whose columns are simply the matrix A times each column of B. A times B1 all the way to A times BP. So that is that when I multiply AB and multiply A times each column, then those become the columns of my matrix AB. Each column of AB is a linear combination of the columns of A using weights from the corresponding column of B. So let's have a look at the sizes of our matrices. We've kind of already looked at this, but we're going to look at it again here. If I'm multiplying, remember that the inner dimensions here need to match in order to be able to do the multiplication, and then the answer will be the outer dimensions. So notice that our answer is m by p. Multiplication of matrices corresponds to composition of linear transformations. So if I start out with my vector x, and I multiply by the matrix B. Then I have B times X. And then we multiply that times A, then we have A times BX, which ends up being the same thing as if I had multiplied X by AB. Computationally, we multiply two matrices by going across the rows of the left matrix and down the columns on the right matrix. So the entry in the ith row and jth column in the product AB comes from the ith row of A and the jth column of B. So in this example, we're going to look at how we come up with this entry by multiplying my matrix A times my matrix B. We'll say that this here is A and then this is B. So we would multiply across A and down B, and we see that we have then 2 times -1 plus 1 times 2. So we have -2 plus 2, which gives us 0. In the same way, we'll look at how we come up with this last entry over here in our answer. We multiply across the bottom row of A and down the last column of B. So I have 3 times 4 plus -2 times 2. So I have 12 plus -4, which is 8. Note that the ith row of AB is the ith row of A times B. So we see here that the second row of AB, which we see here, is simply the second row of A being multiplied by my matrix B. Matrix multiplication has many of the usual properties of multiplication, but some important exceptions. So let's look at this example. We're going to multiply it out, and we're going to use the fact that B is made up of this vector B1 and this vector B2. So I'm going to multiply first my matrix A times my vector B1. So I have my matrix A times my vector B1, and we'll multiply across and down, and we see then that we get -4, -24, and 6. And now we'll multiply my matrix A times my vector B2. So I have my matrix A times the vector B2. And again, we'll multiply across and down. And we get 2, 26, -7. So we know then that when I multiply my matrix A times my matrix B, then I end up with a new matrix where the columns are A times my vector B1 and then A times my vector B2, and that's the definition we looked at. So we see then that AB is simply the following matrix. Now let's look at theorem 2. Matrix A is m by n, and matrices B and C are appropriate sizes for the multiplication we'll look at. So first, we can change the grouping when we're multiplying matrices. If I multiply A times the group B times C, that is equivalent to multiplying A times B, then times the matrix C. I can distribute A times the sum of B plus C is equivalent to A times my matrix B plus A times my matrix C. I can also distribute when I multiply on the right with A as well. If I multiply by a scalar, I can basically move that scalar and multiply it at any point by any matrix and still produce the same answer. I sub m times A is going to be the identity matrix times A. So the identity matrix is simply a diagonal matrix where you have ones on the diagonal and zeros everywhere else. So when I multiply by the identity on the left times my matrix A, I just have my matrix A, and that's equivalent to multiplying by the identity on the right times my matrix A. Now here are the exceptions, and these are very important to take note of. In general, A times B is not equal to B times A. If they are equal, then we say that A and B commute with one another. Number 2, cancellation laws do not hold. If I have A times B equal to A times C, this does not imply then that B equals C. 3, non-zero matrices can multiply and still give 0. So what we mean then is that if I have two matrices multiplying together equal to 0, then that does not mean that A was 0 or B was 0. And this is what we commonly used in algebra. When I was multiplying two things to give 0, then we knew in algebra that that meant one of them was 0. But here's an example where I'm multiplying two non-zero matrices and I get the 0 matrix. Now let's look at powers of a matrix. If A is an n by n matrix, meaning it's a square matrix, then we can multiply it by itself. A squared is A times A. A to the third is A times A times A, etc. We let A to the first power be just equal to A, and we say that A to the 0 power is equal to the identity matrix sub n, since we're dealing with a square matrix n by n. So let's look at an example. I want to raise this matrix to the third power. So I'm going to multiply it by itself 3 times. So first let's multiply the first two, and we see that we get this matrix here. And now I want to multiply that by my original matrix. And we see that we then get this matrix, 1, 0, 21, 8. So you see then that the diagonal entries are simply the diagonal entries from the original raised to that power, but my other entries do not follow any kind of such rule. So we do have to multiply them out. Now let's look at the transpose of a matrix. If A is an m by n matrix, then A transpose, written as the matrix A with a T as a superscript, it is the n by m matrix whose columns are formed from the corresponding rows of A. So here we see our matrix A, and then A transpose, we've simply taken each row of A and turned it into the column of A transpose. So let's look at an example. Given these two matrices A and B, I want to calculate these 4 different values. So first let's multiply A times B. We see that we can multiply it because A was a 2 by 3 and B was a 3 by 2, so the inner dimensions match, and then the outer dimensions will be the dimensions of my answer, so we know we're going to have a 2 by 2. We get the following matrix. Now let's do AB transpose. So we're simply going to take the rows of AB and turn them into the columns of my transpose. Now let's do A transpose times B transpose. So first A transpose is this, and B transpose, so let's look at our dimensions. We have a 3 by 2 now and a 2 by 3, so the inner dimensions match, and we see that when we multiply we'll get a 3 by 3. And this is what we get when we multiply. So now let's look at B transpose times A transpose. We have a 2 by 3 multiplied by a 3 by 2, so we know our answer is going to be a 2 by 2 matrix, and we get this answer here. So we're going to use these to kind of compare. Notice that we ended up with our AB transpose matrix equivalent to B transpose times A transpose. Those two matrices were the same. And that AB transpose was not equivalent to A transpose times B transpose. So then we have the following properties. And this is theorem 3. The transpose of A transpose is back to A itself. The transpose of the sum is just A transpose plus B transpose. The transpose of a scalar times A is that scalar times A transpose. And AB transpose is B transpose times A transpose. So this is what we just looked at in the previous example. The transpose of a product is the product of the transposes in the reverse order. So if A is n by n and B is n by p, then AB is m by p. So AB transpose is p by m. And then B transpose is p by n, and A transpose is n by m. And so we see when we multiply those, we have a p by m matrix. Now you try. I want you to work the next two examples, and we'll discuss your answers in class.